In this video, I'm going to walk you through a strategy for solving two-dimensional problems like projectile problems. And I'm going to introduce you to an approach called XY analysis. In XY analysis, you literally make two columns on your page. You label one of them X and the other Y, and then you use the guess strategy to problem solving twice, once in each column separately. The trick is in realizing that there is often connections between the two columns. In the case of projectile motion, the connection is time. This is because however long the projectile moves sideways in the X direction, it moves for just as long in the vertical Y direction. The motion in the X direction is uniform motion. It's moving at a constant velocity. So the only equation you need to solve the horizontal motion is your velocity is equal to displacement over time. The vertical component of motion, though, is accelerated due to gravity, and so we're going to need our 5 kinematics equations to solve that vertical motion. So let's apply these concepts to a couple of problems. The first problem is stated this way. A dart is thrown horizontally at 16 meters per second toward a wall that's 4 meters away. By how much does the dart drop before it hits the wall? So I usually start with a sketch of the situation, and that will include some information about your coordinate system. So in this case, and in most cases, the ground is considered the zero elevation. And in this case, I have a dart that's being thrown horizontally, initially at 16 meters per second, so I'm going to label that. And it's being thrown towards a wall that is 4 meters away. It's also helpful to sketch the path of the object. And we know that the path of a projectile is a parabolic path, so it might look something like this. When we are interested in the distance between the initial height and the ending height, how far has it dropped, in other words? Anyway, it would strike the wall some unknown distance below where it would have otherwise hit if there were no gravity. So we're going to set up an XY analysis and then proceed with our usual problem-solving guess strategy in each of the two components. So we need to make two columns, one for the X and one for the Y. And we also need to specify what is our positive and negative. And so we're going to say, because all the motion is to the right and down, we're going to say to the right is positive and down is positive. For our initial horizontal velocity, we're given is 16 meters per second. And we're told that it has a horizontal displacement of 4 meters. And that's all we're given. We can list time as an unknown, although it's not specifically what we're looking for in this case. But we also know that we could use the equation for horizontal or for constant velocity, which is written this way. And it looks like we can actually solve for time. So why don't we go ahead and do that? It might end up coming in handy. So time is equal to displacement over velocity, which is equal to 4 over 16, or t is 0.25 seconds. Now in the vertical, we also know the initial vertical velocity. Even though it's going to start falling almost instantly, at the initial moment, there is no vertical velocity. And we all also, of course, know that acceleration is positive 9.8 meters per second squared. And the displacement is what we want to know. But because it's going to stop moving horizontally and vertically at the same time, We've solved for time over on the left side, on the horizontal side, but we can put that in our y column as well. And now we have 3 variables and 1 unknown. We can find a kinematics equation to solve for displacement. Displacement is equal to initial velocity times time plus 1/2 acceleration times time squared. And now what we need to do is substitute and solve. The initial velocity is 0, so we can ignore this term, and we just have 1/2 times 9.8 times 0.25 squared gives us a displacement of 0.306 meters. Let's try another one. A biology textbook is thrown horizontally at 7 meters per second. It's released from a height 1.5 meters above the ground. Find out how far horizontally the book lands on the floor. So again, we start by labeling what we're given. We've got a biology textbook, not a physics textbook. That would be inappropriate. And it is 1.5 meters above the ground. It's going to follow a parabolic trajectory until it hits the ground. And the distance between its initial horizontal position and its final horizontal position is what we're interested in. So let's make ourselves 2 columns of data for the x and the y motion and list what we're given. Let's continue to say that to the right is positive and down is positive. So horizontally, we know that it's moving at 7 meters per second initially. And that's all. We don't have any information about the displacement, which is what we're trying to find. And we don't know anything about time, which we need to solve for displacement. And just as a reminder, displacement is equal to velocity times time. In the vertical direction, we know that the initial velocity is 0. The acceleration is 9.8 meters per second squared. And the displacement, which I'm going to label delta y. This is a new variable, but it's similar to our horizontal displacement delta x. But just to be clear that we're talking about the vertical now, delta y is equal to 1.5 meters. Now it would be helpful to find time so that we could plug that back into our horizontal motion and figure the horizontal displacement. Delta y equals v naught t plus 1/2 at squared. And we're solving for time, so let's rearrange this in terms of time. It's equal to 2 delta y over acceleration. We get a value of t equal to 0.55 seconds, which we can now come back up to this equation, substitute. So our displacement is equal to 7 meters per second times 0.55 seconds, which is equal to 3.87 meters. And that's our answer. Let's look at one more problem where the initial vertical velocity is not 0. In this problem statement, a soccer ball on the ground is kicked, resulting in it leaving the ground at a speed of 50 kilometers per hour initially rising 30 meters above the horizontal. What is the ball's velocity 1 second after it was kicked? So let's set it up in the same way that we've been doing our other problems. First, we'll draw a diagram and label it. And what we know is we have an initial velocity of 50 kilometers per hour, which is equal to 13.89 meters per second at an angle of 30 degrees from the horizontal. We know already now how to break a ugly vector into its x and y components using our trig functions. The x component is equal to the hypotenuse v times the cosine of 30 degrees. And the vertical component is equal to the hypotenuse times the sine of 30 degrees. If we substitute in our values for v, 13.89, times the cosine of 30 degrees, we get a value of a horizontal component of velocity equal to 12.025 meters per second. And likewise, we can solve for the vertical component of velocity, v times the sine of 30 degrees gives us a final vertical velocity of 6.945 meters per second. So now we need to set up our two x and y columns as we've done before and start to write in the variables that were given. But now it's actually going to be more convenient to say that up is the positive direction because that's the direction that our object starts to move in. We can list the horizontal component of velocity that we've already calculated in our x column and our y component in our y column. Again, remember that the x component of velocity is not changing throughout the ball's trip, but the vertical component is changing, and it's changing because of its acceleration, which in this case is a negative 9.8 meters per second squared. This is occurring for a period of 1 second. We don't necessarily know if the ball is on the way up or on the way down, but if we can find the vertical component of velocity at the end of this time period and add that to the horizontal component, then we can find the total velocity at the end of this second. We can use our kinematics equation for the final velocity equal to initial velocity plus acceleration times time. We substitute in our values for vertical velocity and acceleration and time, and we get a vertical velocity equal to negative 2.855 meters per second. So that negative is significant. It means that since we defined up as positive, that this ball is on its way down after 1 second. So now we have both vertical and horizontal components of our final velocity vector. So let's redraw our two components and then draw a resultant. Our x component again is 12.028 to the right. And our vertical component is negative 2.85 down. And the resultant we can find by drawing our vector from the tail of the first vector to the head of the last vector. And the rest is using your Pythagorean theorem and trig functions to find what the magnitude and the direction of this final velocity vector is.